So, hello everyone. I'm Gitanjali Jaina. I'm a PMRF scholar from IIT Delhi. So, I welcome you to the fourth lab section of this course, Physics of Linear and Nonlinear Optical Waveguide. So, in the previous lab section, we have gone through the ray equation in parabolic index fiber, different type of ray equation when the refractive index is different, and what is the effect on the numerical aperture on the refractive index profile, and how the intermodal dispersion is occurring inside the step index fiber. So we have gone through all of this in the previous live session. So in today's live session, we will primarily focus on what are the how the material dispersion is occurring inside a fiber, and what are the different type of how the temporal spreading also occur whenever a pulse is allowed to propagate through a fiber. And besides that, we'll see how we can calculate the spectral width, phase velocity, and the groove velocity for a given refractive index profile. So I will start then. So we'll start from question number one. So which is based on a refractive index profile, and the question asks what are the material dispersion and the zero dispersion wavelength. Okay. So let me read out the question for you. So the question is, for a pure silica, the refractive index variation can be assumed to be given by the following convenient approximate empirical formula. In the wavelength domain, 0.5 to 0.1.6 micrometer. So the expression is given. This is the refractive index profile, which is similar to the Selminier equation. So the constant C0, A, and these are already given. The question asks, what is the material dispersion at 800 nanometer in picosecond per kilometer nanometer? And the second question is, what is the wavelength at which we will see a zero material dispersion inside the fiber? Okay, so we'll start from question A, which asks what is the material dispersion at 800 nanometer in picosecond per kilometer nanometer. So it is asking in terms of this unit. That means it asks about what is dm, which is, if you recall, it is material dispersion coefficient. And if we recall, this is given by lambda by c d square n by d lambda square. So lambda is already given. It is asking to calculate at 800 nanometer. So that means we need to find out what is d square n by d lambda square. Okay. So enough lambda is given, which is C0 minus A lambda 0 square plus A over lambda square. Now if you take the first derivative, dn over d lambda 0. So this is minus A 2 lambda 0 minus 2 A lambda 0 cube. So we have to take the another derivative, d square n by d lambda square, which will be minus 2a plus 6a by lambda 0 to power 4. So that means if you want to find out what is d square n by d lambda square at lambda 0, 800 nanometer means 0.8 micrometer, which which is minus 2A. So what is the value of A? So it is 0.003, 0.003 plus 6 into 0.003 divided by 0.814. And if you calculate it, it will come around 0.037945. Okay, so this is the one part of the value. So for dispersion due to material refractive index, this is given by d tau by d lambda over delta lambda. And tau it is given by, so if you recall, tau is nothing but L by Vg. So, and Vg is L by C. So it is basically, so it is always a good practice if you start from here and see how, so I think I have already mentioned what is DM. Okay. And by using, so it is the way we calculate DM. It's like K depends on omega, then you take the, then you can express it in terms of C omega, n of omega over C. Then take the derivative, then you can find tau is given by L by C, n of omega plus omega dn over d. And in terms of wavelength, it is given by L by C, n of lambda minus lambda dn over d. Now, if you take the derivative with respect to wavelength, then you can easily find out dm will be given by minus lambda by c d square n over d lambda square. So let us put so d lambda is 0.8 micrometer, c is 3 into 10 to the power 5 kilometer per second, and second you can convert it to picosecond, 10 to the power 12, and d square n by d lambda square is 0.037945. It is in micrometer square, inverse of micrometer square. So one micrometer will cancel with lambda, another micrometer you can convert it to nanometer. So this will give 10 to the power 3 nanometer. So the overall solution will be minus 101 picosecond per kilometer nanometer. So while calculation, don't forget to trace back the units. If you take like the wrong unit, then you will get a wrong answer. Okay. So always remember what is the unit you are considering and what is the unit the question is asking about. Okay. And the second one, so let us see. So it was asking about what is the wavelength at which the material dispersion is zero. So material dispersion, if you recall the formula, so this is delta tau, it is given by dm delta lambda into L. So this is the total temporal broadening that can occur due to the material dispersion inside the fiber. And these are all constant. And you can see this delta tau It's directly proportional to d square n by d lambda square. So that means delta tau will be 0 when we have the second order derivative, it is 0. Okay. So we have already calculated what is the second order derivative. So this is this formula, minus 2a plus 6a by lambda 0 to power 4. So let us this minus 2a plus 6a lambda 0 4 equal to 0. So lambda 0 will be is 6a by 2a. So lambda 0 is 3 to power half, which is 1.32 micrometer. So this is the wavelength at which we'll see zero dispersion, zero material dispersion. That means all the waves, that is different wavelengths. So whenever we are feeding a source inside the fiber, it's not like it is propagating through a single wavelength. So it is a spreading. It is a spreading due to the Heisenberg principle. So due to because of the spreading, we will see delta lambda. So, but around this wavelength, all the delta lambda, whatever wavelength is inside this source wavelength, which is delta lambda, they will see zero material dispersion. They will travel at same speed and will reach the endpoint at the same time. Okay, so this is the physical significance. So let us move to our next problem. So the question is asking about what is the group and phase velocity inside the medium because of this refractive index profile. So we have enough lambda 0 is n0 is a constant, a is also a constant. So recall what is the phase velocity is Vp is given by omega by k, right? And you can also write it as a c by n, the speed of light in the vacuum divided by the refractive index of the medium. And n is already given, so that means this will be c by n0 plus a lambda 0. So we have phase velocity, which is c by n0 plus a lambda 0. And for the group velocity, what is the expression? It is d omega by dk. And that means if you want to find out Vg, 1 by Vg, it is dk by d omega. And here you can see, so k is nothing but d by d omega of k0 n of omega, right? 1 minute. And n is expressed in terms of the wavelength of the propagating wave. So that means you have to take the derivative with respect to the wavelength. So you can write it as a dk by d lambda. So d lambda by d omega. And what is the value for this dk by d lambda? So dk by d lambda is nothing but d by d lambda of Is K0 enough lambda, right? So I am showing the different way where you can calculate the dk by d omega. So this is d by d lambda. So that means d by d lambda of K0, if you recall, it is 2 pi over lambda 0 n of lambda 0. And if you calculate the derivative, you will see it is 2 pi d by d lambda of n of lambda 0 over lambda 0. So this is easy for you to calculate now. So because it is in terms of lambda 0, it's better to take lambda 0 here also. Okay. So we will get d by d lambda of 1 by lambda 0 n of lambda 0 plus 1 by lambda 0 d n of d lambda 0. And this will give 2 pi n of lambda 0. This will be minus lambda 0 square. And this will give 1 by lambda 0 dn over d lambda 0. So, and for d lambda by d omega, what we have C equal to omega by K0. That means lambda 0, you can write it as, so put K0 as 2 pi over lambda 0. So lambda 0, you can calculate as 2 pi C by omega. So that means d over d lambda 0 by d omega. So this will come around minus 2 pi C omega square. So we need to express in terms of lambda 0. So that means this. So if you multiply 2 pi C here, this will be whole square over 1 by 2 pi C. And this 2 pi C over omega, it is lambda 0 square over 2 pi C. Okay, so now we have everything for the group velocity. So Vz will be 2 pi minus n of lambda 0 square plus 1 by lambda 0 d of n d lambda 0 multiplied by lambda 0 square over 2 pi c. So 2 pi will cancel. What we have now is 1 by c, and if you put it inside, this will give n of lambda 0 minus lambda 0 dn over d lambda 0. So in this way also you can calculate what is the group velocity in terms of the wavelength. So no need of taking omega first, then again convert omega to lambda. So you can directly take lambda to calculate what is the expression. So what is the question then? Okay, phase velocity inside the medium. When we have n of lambda 0 is a plus b lambda 0. So that means dn over d lambda 0 will be b. So we have the group velocity 1 by c. N of lambda is a plus b lambda 0 minus lambda 0 times b. So this is a by c, which is a constant, right? So Vz is given by a by c. Sorry, this is 1 by Vg, right? So this is 1 by Vg. So that means, and this is already given. This is n0, I think. A is given as n0. Okay, this is n0. This is a lambda 0. That means this will give a. So BZ will be C by A, which is, sorry, C by N0. Sorry for the mistake. So I have replaced B by A and N0 by A. This is A lambda 0 minus A lambda 0. This will give BG is C by N0. This was easy. If you recall the formulas for phase and group velocity, then you can easily calculate what is the um, phase velocity and group velocity. Okay, so in the first part of this session, we'll cover mostly the phase velocity, group velocity. Then we'll slowly move toward the raised transient time, spectral width, as well as what is the material dispersion. So let us move to our next problem. So let me read out the question. For a pure silica, the refractive index variation in the wavelength domain 0.5 to 1.6. It can be assumed to be given by the following approximate empirical formula, which is n of lambda is C0 minus A lambda 0 square plus B by lambda 0 square, where the value for the constant is given and lambda 0 is measured in micrometer. Now the question is asking about calculate the groove velocity at lambda 0 equal to 0.8 micrometer and lambda 0 is 0.85 micrometer, so that the velocity attains a maximum value at lambda 0 equal to 1.32 micrometer. So the first part is to calculate the phase velocity, sorry, group velocity at different wavelength, and the second part is to calculate what is the maximum group velocity that the ray can have. Okay, so we have n of lambda 0, which is C0 minus A lambda 0 square plus B by lambda 0 square. And C0 is already given, it is 1.451. A is given 0.003 micrometer inverts, and B is 0.003 micrometer square. So, what is the expression for group velocity? We have C over the refractive index effective. So, this expression you can write it as a Bg equal to C by N effective. So, in free space or in a uniform medium, we have N effective equal to the N1 or N2. But inside a dispersive medium, this is replaced by N effective, which is N lambda 0 minus lambda 0 dN by d lambda. Okay, so you can remember in this way also. So we have Vz, which is C by N effective, which is C by N lambda 0 minus lambda 0 dN over d lambda 0. So we have an additional term here. So n of lambda 0 is already given. So now we need to find out what is the dn by d lambda 0. So n of lambda 0, c0 minus a lambda 0 square plus b by lambda 0 square. So that means dn over d lambda 0, it will be minus 2a lambda 0 minus 2b lambda 0 cube. So this is the expression, general expression. Let us calculate one by one. So Vg, let us see what is Bg expression now. It is C by n of lambda 0, that means C0 minus a lambda 0 square plus b by lambda 0 square minus lambda 0 times minus 2a lambda 0 minus 2b lambda 0 cube. So first, it's better to calculate what is the final expression, then you can put the values to calculate the group velocity. So this is a lambda 0 square, b by lambda 0 square. This will give plus 2a lambda 0 square plus 2b lambda 0 square. So that means this is c over c0 plus a lambda 0 square plus 3b lambda 0 square. So that means we need to find out only this expression now to calculate the group velocity. So let us see, one is at wavelength 0.8 micrometer and this says C, it is giving. So let us calculate the group velocity in terms of C. So C0 it is given 1.451 and A, I think it is 0.003. B is also 0.003. So A we have 0.003 into 0.8 square plus 2B, 2 into 0.003. Sorry, not, it's 3B and 0.8 square. So just calculate it, you will get, so calculate 1 by this part. So this will give 0.68166. For the next part, we have the same question, but in different wavelength. So this is also, it is same 1.451 plus 0.003, 0.85 square and 3B. Zero 0.85 square. So just calculate it, you will get, this is given by 0.6823C. Okay. And the next part, it was asking about what is the wavelength, what is the, so that the velocity attains a maximum value at lambda 0, at lambda 0 is 1.32 micrometer. Okay. So if you recall, tau is given by L by BAC. Right? So that means maximum group velocity will correspond to a minimum time. So when you consider a pulse, this means maximum group velocity, it will correspond to a minimum dispersion in the medium. So that means now we need to find out what is the minimum value of what is the wavelength that is delta tau. It is minimum. Okay. So delta tau, if you recall, it is directly proportional to dn square d lambda 0 square. So this will be minimum means we have to equate it to 0. So what is d square n by d lambda square? So this is dn over d lambda. So that means d square n over d lambda square. It will be minus 2a plus 6b by lambda 0 to power 4. So it is minus 2a plus 6b over lambda to power 4. It should be 0. So lambda 0 to power 4, it is 6b over 2a. B and A are equal. So now we have 3. So that means lambda 0 is 3 to power 1 by 4 and it will come around 1.32 micrometer. Okay. Now let us move to our next problem. It's here the source is LED. So the question is, consider a LED operating at wavelength 0.85 micrometer with a spectral width of 50 nanometer. At this wavelength, it is already given d square n by d lambda 0 square is 0.0297 micrometer inverse. Calculate the material dispersion in nanosecond per kilometer and comment on the sign of the material dispersion. Okay, so we have LED source. So dm. Now material dispersion in terms of picosecond per kilometer nanometer is given by minus lambda by c d square n over d lambda square. So lambda is lambda 0. It is given 0.85 micrometer and d square n over d lambda square. It is also given, it is 0.0297 micrometer. So let us calculate dm first. So dm is minus 0.85 over 3 into 10 to the power 5, 10 to the power 12. If you convert second to picosecond, and there is 0.0297. There is a micrometer here, you can convert it to nanometer. So that means if you want to convert a form to a picosecond per kilometer nanometer, you have to multiply with 10 to the power 4. So this will give 10 to the power 4. So if you just put the formula, just multiply it by 10 to the power 4, then you can get dm in terms of picosecond per kilometer nanometer. So this will give minus 84 picosecond per kilometer nanometer. And what does the negative sign indicate here? So the negative sign means the higher wavelength, that is towards the red wavelength. This wavelength, higher wavelength travel faster than the lower wavelength. So this is the physical significance of the negative sign. Okay. Now, to get material dispersion in terms of nanosecond per kilometer. So that means we have to multiply dm by the source width, the spectral width of the source, which is given 50 nanometer. And we have to convert picosecond to nanosecond. Okay. So we have delta tau m, which is dm into delta lambda. So it is given by minus 84 into 50. So if you calculate it, it will come around 4.2 nanosecond per kilometer. Okay. So this is the final answer. We'll see why there is a. So initially, the communication it was based on uh, injecting using LED in the optical fiber communication, but when the laser was introduced, gradually we'll see there is because the laser has small spectral width. Because of the small spectral width, we'll see a decrease in the temporal spreading. So because of that, we use laser for the optical communication. Okay. So I think fifth question is also similar to the previous one. So let us quickly solve it. So we have LED operating at wavelength 1.3 micrometer with a spectral width of 20 nanometer, and only the values are different now. So dm will be minus lambda by c d square n d lambda square. So this will give minus. So d square n by d lambda square is minus, so it is positive, and 1.3 over 3 multiplied by 10 to the 4 to d square n by d lambda square is 0.0005. And this will get 2.38 picosecond per kilometer nanometer. And the material dispersion in terms of picosecond per kilometer will be delta tau m, which is dm delta lambda. So dm is 2.38 and delta lambda is given 20 nanometer. This will come around 47.66 picosecond per kilometer. I think all these questions are clear to you. If you have any doubt in between, then you can ask me. Okay. So let us move to our next problem. Please go through the question once. So it's based on the rate transient, the time, so based on the rate transient time. So what is the time required for one period along the fiber axis, or what is the time required for the one-fourth of the uh, one-fourth period of the time. Okay. So we have a step index fiber. It is Refractive index of core is 1.48 and the refractive index of the cladding is 1.46. Now when we incident a ray at an angle, so this will go in a straight line because it's a step index fiber. So what is the time period now here? So time period is the total time taken to travel this distance. Sorry, up to here. And this is the time for the 1/4 of the time period. So the question, it's already given. A is the core radius, it is 30 micrometer. And inside this optical fiber, two discrete rays propagating through it takes time 14.624 and 3.62 to travel one period along the fiber axis. So that means T is given. T1 is 14.624 picosecond and T2 it is 3.62 picosecond. So calculate the angle made by the rays with the fiber axis after transversing one period along the fiber length. So after one period, what is the angle? It remains constant, right? So theta will be theta for one ray. Let's say it is theta I. This theta will remain constant along the fiber axis. So that means we need to find out what is the theta value. Okay, so recall what is the time taken by the ray to travel one period along the fiber length. It is nothing but T is 4 times the TT. And TT, if you recall, this is the time taken for to travel OA distance, right? So if it is theta I, so that means TT is OA by B. And this is OA. What is the velocity? It is C by N1. And express OA in terms of the core radius. So you can get sine theta I, it is A by OA. That means OA is A by sine theta I. So we have N1 A C sine theta I. This is the time for 1/4 of the period. So that means T will be 4 times of dt, which is 4 N1 A C sine theta I. We need to find out what is theta I when T is given. So this is easy to calculate. Let us see the first one. So the first ray, it takes 14.624 picosecond to travel the one period. So we have 14.624, which is equal to 4. What is N1? 1.48. And A is, it's given 30, I think, 30 micrometer. And this C is 3 into 10 to power 8 meter per second. So convert 30 micrometer to meter. This is sine theta. So just rearrange the term so that you can get what is the value for sine theta. this is 4 into 1.48, 30 into 10 to the minus 6, 14.624. So if you calculate it, you will get sine, this will be sine inverse this term, and this will give around 2.32. So that means the ray that takes this much time, 14 picosecond, it is making an angle 2.32 degree with the fiber axis. Now for the second ray, secondary takes relatively lesser time than the ray 1. So ray 2, it takes T2 as 36, how much was it? 3.262 picosecond. To travel the length. So this means this is 4 times T, also 4 N1 1.48, and we have 30 micrometer divided 3 into 10 to the power 8 sine theta I is equal to 3.62 picosecond. So if you rearrange it, you will get theta I is 9.41 degree. Okay. So this is the final solution. So let us see our next problem. So this problem, it is similar to what we have in question number 1 and 2. So it is given n of lambda 0. So this is equal to 1.6 minus 0.005 lambda 0 is 0.002 lambda 0 square. Calculate the group velocity, which is busy at lambda 0.1 micrometer, and find the wavelength at which the material dispersion is 0. So the first is calculation of Vz at 1 micrometer. So as we have seen before, Vg is given by C by N effective, which is C by N of lambda 0 minus lambda 0 dN over d lambda 0. So we have N of lambda 0, so that means dN over d lambda 0, it will be minus 0.005 minus 0.004 over lambda 0 cube. So let us calculate Vg now. So Vg is C over N of lambda 0 minus lambda 0 dN over d lambda 0. At lambda 0 is 1 micrometer. So we have lambda 0, N of lambda 0 is 1.6 minus 0.005 lambda 0 plus 0.002 over lambda 0 square minus, so there is a minus in this term, so let us take plus 0.005 lambda 0 plus 0.004 lambda 0 square. So this will cancel. This will give C over 1.6 plus 0.004 lambda 0 square. So lambda 0 is 1 micrometer. Here. So there is a 0 here. It's not 0.002, this is 0.0002. So that means this is 0.02. It will give lambda 0, 0.0002. There will be 0 here. So if you calculate it, it will come around dVg, it will be 0.624 C. Lambda 0 is 1 here. So this will give Vg is this. Now for the next part, we need what is the wavelength at which we will get a material dispersion of 0 value. So that means we need dn square and over d lambda 0 square. Okay. So let us see. So for material dispersion, is 0 when d square n over d lambda square is 0. So n of lambda, so we have already calculated d of n by d lambda 0, which is this. Minus 0.005 minus 0.00. I think this is 4, right? Because lambda square, it will give multiply by 2. This is 4. So 0.004 over lambda 0 cube. This should be 0. So if you see, there is no lambda term here. Only this will give lambda 0 is 0. That means in this wavelength range, that is, it's given the equation is valid around wavelength. So it is not around wavelength 0.5 to 2 micrometer. So in this wavelength region, we don't have any wavelength that will give a material dispersion of 0 value. Okay, so it's not possible to have 0 material dispersion inside this range. Is the 2 micrometer. So it's not possible to have a 0 dispersion. Let us move to our next problem. So the question is, what is the spectral width of a pulse, which corresponds to a bandwidth of 12,500 gigahertz around wavelength 1550 nanometer in the low loss window of silica-based optical fiber. So there is a pulse which has bandwidth is already given. Bandwidth is 12,500 gigahertz around, and this bandwidth corresponds to a central wavelength of 1550 nanometer. Now the question is asking about what is the spectral width of a pulse. Spectral width means delta lambda. So so we need to find out what is the delta lambda for this case. So how you can calculate it? So it's based on the fundamental relation between the frequency and the wavelength. So in free space we have C equal to frequency into lambda, right? So that means you can write lambda as C by A. So this will give delta lambda as, take the derivative in the other side, it will give minus C by F square delta F. So now if you want to express in terms of the given parameter, so what is given? Bandwidth is nothing but delta F and lambda 0 is given. So that means we need to express in terms of lambda 0 and delta F. So what you can do? You can multiply C and divide it by C. C by F, it will give lambda 0 square over C delta. So now we know all the parameter. Lambda 0 is given, delta F is given, and C is the speed of light in the medium, in the vacuum. So let us see. So delta lambda, it is given by, so mode of delta lambda is lambda 0 square over C delta F. And lambda 0, it is 1550 nanometer. So 1550 nanometer square. Delta F is 12,500 gigahertz. So this is 10 to the 9 hertz, right? And this is 3 into 10 to the 8 meter per second. And lambda 0 square by C. So, it's given 12,500, 1050 nanometer. Okay, so to cancel 1 nanometer square here, this is 1550 is in terms of nanometer, right? This will give nanometer square. So to cancel it, we need to convert the meter here to nanometer. So that will, it will be 10 to the 9. So 1 meter is 10 to the 9 nanometer. So this will give, this will multiply a factor by 10 to the 9. And this whole will give a value delta lambda 0 is 100 nanometer. Okay. So that means for this bandwidth, we have spectral width delta lambda is 100 nanometer. And it typically corresponds to LED type of source. Okay. So let us move to our next problem then. So the question says consider a Gaussian pulse of initial width 5 picosecond propagating through a dispersive material with decay over d omega is 1.53 into 10 to the minus 3 second per meter. At the operating wavelength lambda 0 is 850 nanometer. Neglect all the higher order terms. What is the temporal spread in the pulse after it travels through a distance 5 kilometer inside the dispersive medium? So what is the spreading when it travels through a dispersive medium? So if you recall, we have the pulses in terms of the wave packet. Later we'll see that inside this wave packet also there is a variation of the frequency, which is known as chirping. So we have this pulse. Now it propagates through a dispersive medium. Propagation in dispersive medium. So inside the dispersive medium, what will happen? The amplitude may decrease and that there will be a spreading of the pulse depending on the type of dispersion. So amplitude may decrease. So let us say we have here psi t as psi 0 e to power minus t square by t 0 square e to power minus I omega 0 t. And it is already given the k is k omega 0 plus 1 by bg omega minus omega 0. And we neglect all the higher order terms. So what is psi of zt now? This is given by psi 0 t 0 over root pi minus infinity to infinity e to power minus omega by omega 0 square t 0 square divided by 4, and there is a e to power I kz minus omega t d omega. And when we consider the dispersion, the expression, the Taylor series expression up to this happen. Okay. So up to first order, that is if k of omega, if it is given up to first order, that is k omega 0 dk by d omega, which is 1 by vg omega minus omega 0. So up to first order, if you recall in the lecture, there is no spreading of the pulse. So whatever the temporal width of the initial pulse, after propagation also it will have the same temporal width and the same uh, amplitude. Okay. So this will give no broadening. This has been discussed in the class. Okay, so only when the higher order terms, like higher order than dk by d omega, when it comes into the picture, then we'll see there is a temporal spreading in the pulse as well as there is a decrease in the wave amplitude. Okay, but for now, for this case, there will be no, there is, there will be no further spreading in the pulse. So that means if the initial pulse has temporal width, which is T0, so after propagating through the medium, it will have T0. Okay, so this is a conceptual question. If you remember the concept, if you know the concept, then you can easily find out what is the temporal spreading for this case. Okay, so we'll move to our next problem then. So till now, do you have any query? Right. Okay, no question up to now. So, okay, let us move to our next problem then. So it's also the next problem, it is also a conceptual one. So it is given, consider a Gaussian pulse of amplitude psi 0 and temporal width T0 is propagating through a medium showing normal dispersion. Okay, so we have a pulse which is amplitude psi 0 and temporal width T0. And it is propagating through a normal dispersion medium. So now it is propagating through a medium which show normal dispersion. The same Gaussian pulse is made to pass through a second medium showing anomalous dispersion. So that means now it is made to propagate through a anomalous dispersion medium. Then how does this medium affect the amplitude and temporal width of the incident Gaussian pulse? And okay, so it is asking about after propagating through these two different medium, what will be the psi 0, what will be the effect on psi 0 and what will be the effect on T0. So if you recall, what is the normal dispersion condition for normal dispersion? It is the group velocity dispersion coefficient. It should be greater than 0 for normal dispersion. And for anomalous dispersion, we have beta 2, it is less than 0. So now, and if you recall, when it propagates through a medium, the amplitude may decrease. So this amplitude psi 0 tilde, it is given by psi 0 over 1 plus 2 beta 2 z T0 square whole square half. This is the effect on amplitude and the temporal width. So temporal width, it is given by T0 tilde, which is T0 1 plus 2 beta 2 z over T0 square half. So for medium 1 and for medium 2, this is beta 2 greater than 0, this is beta 2 less than 0. So if you see the formulas for the amplitude as well as T0. So this formula involves beta 2 square. So that means whether the sign is positive or whether the sign is negative, it doesn't matter. They will have the same amplitude and they will have the same temporal width. Obviously, after propagating through the medium, if beta 2 is non-zero, then there will be a decrease in amplitude and there will be increase in temporal width. But in both the medium, they have the same magnitude. So what I mean, the psi 0 will decrease by the same magnitude. And this decrement, it is maybe due to the attenuation, different type of absorption that is happening inside the medium when it propagates. Okay, so will decrease by same magnitude in both the medium, and this magnitude is 1 over 1 plus 2 beta 2 z over T0 square whole square half. Similarly, psi 0 will decrease, but T0 temporal width, it will increase. This will increase by same amplitude, same magnitude in both the medium, which is given by 1 plus 2 beta 2 z over T0 square whole square. Yes. Okay. So these are the answers. So let us see our next problem. So it's based on a uh, refractive index profile, which is the expression like this. So a pulse of light with a spectral width delta lambda 03 nanometer propagating through a material with a refractive index given by n of lambda 0, which is 1.48 plus 0.0015 lambda 0 square minus this. And the operating wavelength is between 0.7 to 1.9 micrometer. So first part is to calculate the material dispersion coefficient D at lambda 0 equal to 1.5 micrometer. And the second part is if the initial pulse has a temporal width T0 is 2 picosecond, then what is the final pulse width after propagating 20 kilometer through the dispersive material? So the question is telling about consider the group velocity dispersion. Okay, so let us see the first part, which is to calculate the material dispersion coefficient. This is material dispersion coefficient, which is dm. So we have dm, which is lambda 0 by c d square n over d lambda 0 square. So n of lambda 0 is given, is 1.48 plus 0.0015 over lambda 0 square minus 0.0015 0.00005 lambda 0 square. So just calculate the dn square by d lambda square. So dn over d lambda 0, it will be minus 0.0015 over lambda 0 cube plus 4 into 0.00005 lambda to power 5, which is minus 0.003 over lambda 0 cube plus 0.0002. So we need to take uh, another derivative, which is d square n over d lambda 0 square. This will give minus, so minus minus will be per plus. So this is 3 into 0.003 over lambda 0 to 4. And this will give a minus 5 into 0.002 over lambda 0 to 6. So this is 0.009 minus 0.001. What is lambda 0? It is given, it is 1.5 micrometer. So that means we need to calculate d square n over d lambda 0 square at lambda 0 1.5 micrometer. So this will be 0.009 1.54 minus 0.001 1.56. And if you calculate it, it will come around 1.69 into 10 to the minus 3. So that means we have dm now as minus lambda 0, it is 1.5 by c, it is 3. So we have to multiply it with 10 to the 4 so that we can get a value in picosecond per kilometer nanometer. And d square n by d lambda square is 1.69 into 10 to the minus 3. And this will give a value minus 8.45 picosecond per kilometer nanometer. So we have dm now minus 8.45 picosecond per kilometer nanometer. This is the first part of the question. Now for the second part, let us see. For the second part, it is asking if the initial pulse has a temporal width T0 as 2 picosecond, then what is the final pulse width after propagating 20 km through the dispersive material? And to calculate the pulse width, it is saying consider the groove velocity dispersion. So ignore the material dispersion, only consider the groove velocity dispersion and find out what is the final pulse width after propagating 20 km. Okay, so let us see. We have T0 is 2 picosecond. And if you recall, so what is the group velocity dispersion coefficient? So group velocity dispersion coefficient, it is given by beta 2, right? Beta 2 is the group velocity dispersion coefficient. This is d square k over d omega square. And in the formula, it is not given. D square k by d omega square, it is not given to us. But if we recall the lecture, there is a simplified form for the d square k by d omega square. That is by expressing k in terms of lambda and omega in terms of lambda. Okay. So if you recall, it is 1 by c d by d lambda of n minus lambda dn over d lambda, and is d lambda by d omega. So this we have, so this is like 1 by vg, right? So this is nothing but d by d omega of dk by d omega, right? So this is d by d omega of 1 by vg. So we need to express in terms of lambda. So this is d by d lambda 1 by vg, and this is d lambda over d. So this is what written here. Vz you 1 by vz you already know, it is expressed in terms of n minus lambda dn by d lambda by c. And if you simplify it, because all the terms are in terms of wavelength, so if you simplify it, you will get this is lambda q over 2 pi c square d square n over d lambda square. So this is the expression for the group velocity dispersion coefficient. One thing we know in the question is dm. So dm we have already calculated. So if we somehow relate the beta 2 with dm, then we can easily find out what is the uh, group velocity dispersion coefficient for this case. Okay, so dm, it is, if you recall, dm is minus lambda by c d square n over d lambda square. Now if you divide beta 2 over dm, what will you get? So this is lambda q 2 pi c square d square n by d lambda square over minus lambda by c, and it is d square n over d lambda square. So this will give lambda square minus lambda square over 2 pi c. Uh, huh. This will give this. So that means beta 2, it will be minus lambda square by 2 pi c d. And the unit will be picosecond square per kilometer. This is beta 2. And we know dm 2 pi c, we can calculate lambda, lambda is also we can calculate. So because of the group velocity dispersion coefficient, what is the temporal width? So what is the expression for temporal width? So we have T0 tilde for the group velocity dispersion. So which is nothing but T0 1 plus 2 beta 2z by T0 square over square half. This is the temporal spreading because of the group velocity dispersion coefficient. So if we have considered the material dispersion also, then there will be a term because of the material dispersion also. But in the question it is given to ignore, to only consider the group velocity dispersion coefficient. So that is why we are calculating this. Okay. So Z is already given. It is 20 kilometer. T0 is also given. I think this is 2 picosecond. Yes. So this is 2 picosecond. So our only job is to find out what is beta 2 here. So beta 2 is given by minus lambda square over 2 pi c dm. So what is the value for dm? It is minus 8.45 picosecond per kilometer nanometer. So dm we have minus 8.45 picosecond per kilometer nanometer. And lambda, it is, what is lambda? Is 1.5 micrometer, right? Lambda is 1.5 micrometer. So that means here you can take minus 1.5 into, so we need to express one wavelength in terms of kilometer so that it cancel with the, so that we can get beta 2 in terms of picosecond square per kilometer. Okay, because here you can see beta 2z, it should have the dimension of T0, right? So beta 2z should have dimension of T0, which is picosecond. Uh, picosecond square, T0 square, right? So that means the beta 2, the dimension we should calculate beta 2 in terms of picosecond square per kilometer. So that is why we are making a unit conversion. Okay, so this will be 1.5. So you can calculate it, 10 to the minus 12, 8.45 over 2 pi is 3.14. It is 3 into 10 to the power 5, and there will be 10 to the power minus 12 here. So I just change the unit so that we can get in terms of picosecond square per kilometer. Okay. So this will give a value 1 into 10 to the power minus 5 picosecond square per kilometer. So that means now we can easily calculate what is T0 tilde now. So T0 tilde will be T0 1 plus 2 10 to the power minus 5, and Z it is given 20 kilometer, and T0 square will be 4 square per 1 by 2. Here you can see this term, it is much less than 1. So that means this T0 tilde will be T0 only. That means this is 2 picosecond. Okay, why is it like this? Why we get a 2 picosecond after it propagates to the 20 kilometer fiber? So whenever it enters the dispersive medium, so we'll see dispersion. Okay. But here we'll see up to certain distance, the dispersion effect is negligible. This is T0 square. So this expression itself says T0 tilde will be T0 when this term, when this beta 2 Z by T0 square is much less than 1. So when it is negligible, then we can ignore it, and uh, the temporal width will be equal to the original width. So that means Z here is much less than T0 square by 2 beta 2. And if you calculate T0 square by 2 beta 2, it is 4 picosecond. And what is beta 2? Beta 2 we get 10 to the minus 5, right? 10 to the minus 5 to per kilometer picosecond square. So this gives a value of 2 into 10 to the 5 kilometer. So this condition says whenever the propagating distance, it is less than, much less than 2 into 10 to the 5 kilometer, then the temporal spreading will not be there. So the wave will propagate undistorted. There won't be any change in the amplitude and there won't be any change in the temporal width. So in the question it was given 20 kilometer, right? So this is much less than this distance. So here you can say this will have the same temporal width as well as the same amplitude. Okay. So in this way you can easily calculate up to what distance the wave can propagate undistorted. Now let us move to our next problem. Please go through the question once. So the question says, in the first generation optical communication system, one used LEDs with lambda 0 equal to 0.85 micrometer and delta lambda is 25 nanometer. Okay, so in the first generation, we have LEDs that are used for optical communication and given at lambda 0. So first generation works around this wavelength, 0.85 micrometer, which is the dn square by d lambda square is 0.03 micrometer inwards for pure silica. So calculate the broadening in the pulse due to the material dispersion. So how you can calculate? So broadening due to the material dispersion. This is nothing but the material dispersion coefficient multiplied by the source width, delta lambda 0, right? So all the parameters is given for dm. So dm is minus lambda 0 by c d square n over d lambda 0 square. All the parameters are given, then you can easily calculate what is dm for this situation. So lambda 0 is given 0.85 micrometer and d square n over d lambda 0 square, it is 0.03 micrometer inwards. So we have dm now, which is minus 0.85 into 10 to the 4, 0.03 over c, right? So this is 3. So this will give minus 85 picosecond per kilometer nanometer. And delta lambda, it is already given. It is 50, 25 nanometer. So that means that broadening due to the broadening due to the material dispersion will be dm times delta lambda 0, which is minus 85 into 25. So this will give minus 2125 picosecond per kilometer, which is nothing but minus 2.1 nanosecond per kilometer. So in the first generation, we have LED, which has higher value of delta lambda 0, and the dispersion, the material dispersion will be around 2.1 nanosecond. So now let us see what will happen when we use laser instead of LED. So in the fourth generation optical system, which we used up to now, so we use laser diodes at wavelength 1.55 micrometer at delta lambda 0 is 2 nanometer. So we can see how narrower the pulse is. So previously we have 25 nanometer, here we have 2 nanometer. And it is already given d square n by d lambda square is this for the silica based fiber. Then calculate the broadening in the pulse due to the material dispersion. So this is similar, but here we'll see the broadening will decrease when we use laser instead of LED. So this is minus lambda 0 by C d square of d lambda 0 square. The wavelength is 1.55 to 0.0042, and we have to multiply it with 10 to the 4 by 3. And this will give 21.7 picosecond per kilometer nanometer. So what will be delta lambda now? Sorry, delta tau. So delta tau will be dm multiplied by delta lambda 0, which is 21.7 into 2 nanometer, which will come around 43 picosecond per kilometer. So here we have 2.1 nanosecond per kilometer, but here if you see, we have 43 picosecond per kilometer. So that means the temporal broadening inside the when the wave propagates, it is now decreased because we have used laser, which is narrower spectral width. And other thing is we have operated in the low loss optical window, which is 1550 nanometer. Okay, so this is the question. Now we'll solve the next problem. This will be last problem of our session. So we have a temporally asymmetric chopped Gaussian pulse of the form psi of ZTS, be it were, so let me write. So psi of ZT is B it were minus T square by T0 square 1 plus I gamma T it were I omega 0 T minus K0 Z. So for this chopped pulse, what is the spectral width of the pulse? And if you recall how you can calculate A of omega when you are given psi of ZT. So the formula is A of omega. It is given by 1 by 2 pi psi of 0t e to power minus I omega t dt. minus infinity to infinity. So psi of zt is given. So we can calculate what is psi of 0t now. So which is psi of 0t will be b e to power minus t square by t0 square, and it is 1 plus I gamma t e to power I omega 0t. This is psi of 0t. So A of omega, it will be 1 by 2 pi minus infinity to infinity b e to power minus t square t0 square 1 plus I gamma t e to power I omega 0 minus omega t dt. So we have, what is the exponential part? We have minus t square by t0 square 1 plus I gamma t plus I omega 0 minus omega t. This you can write it as so you can write it as t square over t0 square plus I gamma. There will be minus right here. Minus I omega I gamma t cube over t0 square plus I omega 0 minus omega t. So here you can see in addition to t square, we have a tq term here, right? So to calculate the integration for this, we don't know the standard formula. But what we can do, gamma here is the perturbation. When gamma is small, then you can write for, let us say we have small values of gamma. So for this we can approximate the term which is e to the minus I gamma t q over t0 square. So this is approximately equal to 1 minus x is I gamma t cube over t0 square. So that means we have A of omega now is b over 2 pi minus infinity to infinity e minus t square t0 square and plus I omega 0 minus omega t, and there is a term, approximate term, which is 1 minus I gamma tq over t0 square dt. So just separate the terms. We have b by 2 pi. One term will have minus infinity to infinity e to power minus t square t0 square plus I omega 0 minus omega t dt, and the other part, so I have just multiplied this with the terms. Other part will have minus I omega gamma t0 square minus infinity to infinity dq e to power minus t square t0 square plus I omega 0 minus omega t. So let us solve term by term. So let us say this form is I1, this is I2. So I1 you can easily calculate it because it is similar to what we have seen in the lecture. So I1 is minus infinity to infinity e to power minus t square over t0 square plus I omega 0 minus. So it is in terms of e to power minus alpha x square plus beta x, right? So the value will be root over a pi by alpha. Alpha is 1 by t0 square. So this will give t0 and e to power minus beta square by 4 alpha, right? So this will give omega 0 minus omega square by 4. Alpha is t0 square. So we have calculated what is the first part of the integration, which is this. Now for the second part, what you can do, I2 is I omega t0 square minus infinity to infinity tq e to power minus t square t0 square plus I omega 0 by omega dt. So for this part, what we can do, we have a cube term of t and we have a term which integration we already know. So that means you can solve it by integration by parts. So just use the integration by parts rule. So if you use it, you can get I2 is. So I am leaving this to you to calculate. So this will be I omega t0 square 3 t0 4 by 4 root pi e to power minus t0 square omega 0 minus omega square by 4. So now we have I1 and I2. That means E of omega will be B by 2 pi I1 plus I2. So this is B by 2 pi root over of pi t0 e to power omega 0 square by 4 minus there is a term I omega t0 square t0 to the 4 by 4 omega 0 minus omega multiplied by root over of pi t0. So here you will get a t0 also e to power minus t0 square omega minus omega 0 square by 4. Okay. This one seems complicated because it has a term which is proportional to dq. So this is the approximate formula for the spectral width. So this is the approximation that we have made when we have gamma is small. So I hope the question that I've solved it covers whatever there in the assignment 4. So if you go through the question, then I think you will be able to solve the problems that has been posted in assignment 4. Okay. So do you have any query So if you have any query, then I can clarify now. Otherwise, we'll end the live section for today. So I was going through the exercise that we saw in the first section. Problem 14, 15. When we solve for k, we just solved for the direction of k, but didn't find the magnitude of k in the new medium. 14 and 15. So you are talking about the tutorial or the means the things that I have solved. 14, 15 means theory only. Okay. So let me see. Tutorial first exercise section means tutorial 1. This one, I think. Okay. 14 and 15. What was the question? What is the expression of, is this the question you are talking about? 14? Okay. So consider a express electromagnetic wave of frequency omega in traveling from a medium of refractive index 1.5 to a medium of refractive 1. The wave is incident on the visor plane. It's vertical. So then what is the expression for the transmitted field? Direction, okay, but didn't find the magnitude in the neighboring. So magnitude you can calculate it. Yes, I haven't calculated the magnitude because the question was talking about what is the expression of transmitted field. So magnitude, you can calculate it because KT we have already calculated it. So and Z and K. So you already know that Z cap and K cap they are orthogonal. So that means KT, the magnitude of KT will be root over of ky square plus kz square, right? So the wave is propagating in the yz plane. So just take the square of, so let me calculate then. Uh, Magnitude of kt. Kt will be square root 0.75 square. There will be k0 plus 0.66 square. Okay. So what will be the value for this? Shouldn't the K0 be adjusted for the new medium? Adjusted consideration medium of refract is 1.5 to 1. Okay. So I think you are talking about shouldn't the K0 adjusted to means KT should be equal to K0. I think you are talking about that, right? So you are asking if the wave is propagating from a medium of 1.5 to a free space, then kt should be equal to k0. But if you calculate it, it's like here you only get k0 only because it the square will come around 0.999, which is approximately equal to k0. So it is equal to the free space wavelength. Sorry, free space wave vector. You are right, because when we move to a free space, then kt should be equal to k0. This you can see from the by taking the, so this terms, the square term will come around 0.99, which is approximately to 1. Okay. It's a nice observation that you should have kt equal to k0, and you will get also. Okay. 15, I think 15 also it's the same. For 15, it's like a, so it's a, I think, decaying wave. It's the evanescent wave, the z direction. Okay. Okay. I hope I have cleared all of your questions then. Do you have any other query? So I haven't uploaded the, I think for question first exercise, I have already uploaded the means the file. YouTube videos are already uploaded, but the files for 2 to 3, I think it's not uploaded. So I will upload that today. Okay. So please go through the questions. And if you have any doubt, then I will talk about it in the next live session. So thank you for joining the live section. I hope whatever I have solved, it is useful to you, useful for you to solve the assignment. And so we'll meet on next Monday, same time from 6 to 8. Okay. So thank you. So let me end the section.